Hi, everyone. Thank you so much for attending the presentation. My name is JiayiZhang. I'm a PhD student at the University of Pennsylvania. Today, I'll be presenting our work on building automated detectors that detect smart model cognitive operations in mathematical problem-solving process. This work has been done in collaboration with members from UPenn, University of Minnesota, and QThink, the platform where we collected the data from. I will start off by talking a little bit about self-regulated learning, SRL, its measurements, and some of the challenges it has. An increasing body of work has shown that self-regulated learning, SRL, is a critical component of learning, and it is positively associated with learning outcomes, especially in mathematics problem solving. Students who are skilled in SRL are able to effectively set goals, search for information, and direct their attention and cognitive resources to align their efforts with their objectives. As a result, SRL facilitates the successful problem-solving process and it enables students to acquire a deep and conceptual understanding of the embedded knowledge. Because of the benefit, we want to facilitate students' use of self-regulation in the problem-solving process, and in order to do that, we need to be able to first measure it. We want to know if students are self-regulating during the problem-solving process and what SRL strategies that they are using, etc. Currently, there are 3 approaches to measure SRL. The first one is self-report, which involves the use of pre- and post-survey that ask students either to plan or recall their use of SRL. The second approach is think out loud, which asks students to verbalize their thinking as they are working on a task. Both of these approaches, as we can tell, are very labor-intensive. Therefore, it is not ideal to provide measurement at scale. Hence, the third approach, using log data to measure SRL, has been gaining traction. Using log data, several previous studies have identified behavior patterns that resemble the use of self-regulation and developed detectors to flag behaviors such as setting goals, gaming the system, or planning and tracking progress. Most of these detectors are detecting high-level SRL strategies that combine several behaviors together that are normally treated as separate in SRL theories. In our study, because of the rich log data we collected, we were able to build detectors at a finer grain size and ground our work in SRL theory. As such, it is our goal to build detectors that can be used in theory-driven intervention. Therefore, in the current study, we built automated detectors of SRL construct from a theory-driven lens. We first collected data from QThink, an online math learning platform. We examined the learning environment, understanding how students interact with the platform and the context of where the log data is generated. Based on the context and the log data available, we chose Winnie and Hadwin's smart model as the theoretical grounding. We identified 5 SRL indicators relating to 2 cognitive operations in the smart model, which I will talk more in a later slide. We then trained machine learning models to detect the presence of the 5 indicators. In the end, we report the model's performance and evaluate the performance across student population to ensure the model is fair. Now let's take a look at the platform QThink. So QThink is a digital learning application that focuses on enhancing middle school student math problem-solving skills. The program encourages students to engage in self-regulated learning and to develop math language to communicate problem-solving process. And here is a video clip of how they describe their platform.
Application-based problem solving is prevalent in all types of learning and high-stakes assessments. Are you looking for a problem-solving toolkit to help your students organize their thinking and better communicate your ideas? QThink, a web and tablet application, enhances the problem-solving experience for all your students. Using QThink, your students create a thinklet which showcases their problem-solving process as they understand, plan, solve, and review a problem. Starting with understand, students observe, puzzle over, and estimate. You really can't solve a problem you don't understand. In the plan phase, students select a strategy to use and plan how they will use it. To solve the problem, students use tools to create drafts, think alouds, and final presentations. And in the review phase, they self-reflect to make sure their math makes sense and communication is strong. Together, students create a thinklet that captures and shares their entire problem-solving process.
Okay, so to quickly sum up, we know that QThink structures a math problem into a thinklet. Within each thinklet, the problem-solving process is scaffolded into 4 phases, which are understand, plan, solve, and review, as shown as the 4 panels in the screenshot. Within each phase, students are asked to answer several questions or to complete a task, and these questions are outlined on the right side of the slide. For example, in the understand phase, after reading the math problem, students are asked about what they noticed, what they wonder, and what their estimated answer is. And in the plan phase, students are encouraged to select the strategies that they're going to tackle the problem with and to write down their plan of how they will solve the problem. We collected students' text-based responses to all the questions within a thinklet, and the screenshot on this slide is an example of process log data that we collected of a student's work in a thinklet. As we see, each row is a student's response to a question. With the log data collected, we then proceed to building automated detectors, which involves the following 4 steps, which are construct operationalization, coding the data, feature distillation, and training the models. First, construct operationalization. In this step, we identified 5 SRL indicators relating to 2 cognitive operations in Winnie and Hudwin's SMART model. The reason that we chose SMART model as the theoretical grounding in our work is because it looks at SRL at a finer grain size. Specifically, it outlines the cognitive operations involved in the problem-solving process, which are searching, monitoring, assembling, rehearsing, and translating. Each operation describes a way of how learners cognitively engage and interact with information. In our work, we focus on the assembling and translating, as they are frequently employed in the initial stages of problem solving when learners define tasks and set goals. Through an iterative and collaborative process between the research team and developers at QThink, we outlined and operationalized 5 SRL indicators presented below, which are numerical representation, contextual representation, strategy orientation, outcome orientation, and data transformation. The first 2 indicators concern how learners present a problem, so problem representation. In student text-based responses, when learners assemble the numerical components from the math problem and demonstrate a level of understanding of how the numerical values are used, we consider that as evidence of numerical representation. Similarly, if contextual details are noted in students' responses, we consider that as evidence of contextual representation. Strategy and outcome orientations are indicators that consider how students set their goals and form plans for the problem-solving process. Students who demonstrate the use of strategy orientation focus more on explaining how they will find the answer, while students who use outcome orientation focus more on what they believe the answer will be. Lastly, data transformation reflect behavior that are associated with translating operation, in which the learner manipulates the ways information is presented to them in the problem in order to find a solution. So, in a way, the 5 indicators identified in our work not only demonstrate the fact that learners are engaged in SRL, but also shows what cognitive operations learners are using and how they're using them. Okay, moving on to the next step, coding the data. So everything we just discussed, such as how we operationalize construct, happened in the preliminary coding phase, where 2 coders went through several thinklets together, read through student responses. Using grounded theory, they identified the 5 SRL indicators, operationalized them, and created a rubric for later coding. With the rubric, the 2 coders coded the same set of data separately. They then compared their coding and computed the inter-reader reliability kappa. As we see in the bar graph, the two coders reached an acceptable kappa above 0.6 for all 5 SRL indicators. Once the reliability was established, the coders move on to the individual coding phase, where they split the rest of the data and coded them individually. Now let's move on to the feature distillation step. So altogether, we designed and engineered 100 features and extracted them from each thinklet. These features included ones that are distilled on the thinklet level, for example, the number of questions students answered in a thinklet, or the number of questions students answered in each phase, that is the understand, plan, solve, and review phase. We also designed a set of features that examine the content and the linguistic features of student text-based responses. So these features were first extracted at the response level and then aggregated to the phase level. For example, in each response, as shown as the rows in the screenshot, we examined, for example, the length of the text, the number of words, nouns, pronouns used, if the text contains a numerical value, if it contains any keywords, or how similar the text is to the problem item, etc., etc. This information then, as mentioned, aggregated to the phase level using mean, standard deviation, and max. Again, altogether, we extracted 100 features from each thinklet, and these features were then used to train the model. With the ground truth data collected from human coders from 182 thinklets and features distilled from the same set of data, we trained models using XGBoost to predict the presence of the 5 SRL indicators. We evaluated the model using tenfold student-level cross-validation and computed the average AUC ROC of each model. And here is the performance of our models. Because of the rarity of strategy orientation, specifically, we only have 8% of data that shows the use of strategy orientation. A model could not be built for this indicator. However, all the other models perform pretty well and have reached an average AUC ROC about 0.75. To better understand our detectors, as well as to inform our understanding of how these features relate to the construct, we calculated the SHAP value of each feature to reflect their importance in the models. In the paper, we reported the top 5 features from each detector. We also give an interpretation on how these features are related to the construct that we're detecting. Because of the time reason, I'll not go into details naming all the top features, and instead in the presentation, I'll give a high-level overview and a couple examples of what features were used in the detectors. But I highly recommend people to check out our paper for those who are interested in learning more. First, we find that most of the top features in the 4 detectors are from the understand and the plan phase. And this finding makes sense because these 4 detectors are related to the 2 cognitive operations, assembling and translating, that are frequently employed in the initial stages of problem solving. That is when learners define tasks and set goals. And the understand and the plan phases in QThink are specifically designed to help students to scaffold the process of defining tasks and setting goals. Therefore, it is reasonable to see that most of the important features in the detectors are from these 2 phases. Next, numerical representation detector. We see that this model relies on features that examine the numerical values used in the understand phase, as well as features that compare the similarity between student response and the problem item. The numerical value feature makes sense as the detector is operationalized to identify numerical components that are processed and used when students assemble information. However, the maximum similarity feature, a feature that takes both numerical values and text into account, also contributes to the numerical representation detector. This finding suggests that the numerical representation detector not only examines if numbers are used in student responses, but also how they're used in relation to the problem. In the contextual representation detector, the model relies on features related to the keywords used in the understand phase and the length of the responses in the plan phase. The latter one, the length of the responses, indicates the relationship that the longer the responses are when student is forming a plan, the more likely it is for the student to contextually representing the problem. Similarly, we find that keyword use and the use of numerical values are positively related to outcome orientation. And student selection on strategies and the length of their responses positively predict their use of data transformation. Again, for the extensive list of top features and the interpretation, please feel free to check out our paper. Lastly, to ensure our model is fair and free from algorithmic bias, we checked how the models perform across student populations. Using predictions made in the test set, we computed the AUC ROC for the following gender and racial ethnic groups listed in the figure below. In each detector, relatively small differences in AUC ROC were observed across gender and racial ethnic groups. For example, as the bar graph shows, the numerical representation detector does not perform drastically different across the 3 gender groups and the 6 racial ethnic groups, either compared to the overall AUC ROC or compared across student populations. And we observed a similar pattern for the other 3 detectors as well. Additionally, we found no student group, either gender or racial ethnic group, consistently had the best performing detectors. So overall, we're happy to say that our detectors don't seem to have an algorithmic bias issue. And that is essentially everything we did in this project, but there are a couple of things that we'd like to do in the future. The first one is using this theory-driven approach, we want to build more detectors to detect SRL construct relating to two other cognitive operations so that we can understand students' use of SRL from different perspectives and their use of SRL at different stages in the problem-solving process. Additionally, we would like to conduct more correlation analysis to understand how these SRL indicators are related to engagement, performance, and learning outcomes. This set of analysis will help us to answer questions like, if students are using numerical or contextual representation, are they more likely to get the question right, etc. These results will be critical, serving as the premise when designing interventions that promote the use of SRL. Lastly, we're actively working with teachers and developers at QThink, hoping to implement the detectors into the platform so that these detectors could provide more real-time feedback, which will enable the possibility for teachers to provide more timely interventions. And that is everything. Thank you so much for listening. I would like to thank my collaborators and AirDev who funded the project for making the paper possible. If you have any questions or comments, please feel free to send me an email at joycez@upenn.edu. Thank you.